Good day and welcome back for the second part of our discussion on Lagrange multipliers. And let me begin with just a quick reminder. Lagrange multipliers are used to find the absolute maximum and minimum values of some function subject to a constraint equation. For example, if we look below, the function given by a equals 2xy plus 2yz plus xz is actually representing the surface area of an open top box. And it is subject to a constraint related to the volume of the box. So in words, we'd be saying what is the maximum or minimum surface area of an open top box whose volume is 4. Now, in order to use Lagrange multipliers, there is an equation that we have to recall. These maximum and minimum values occur precisely when the gradient of f is equal to lambda of the gradient of g. And if you combine together all of the individual components of this gradient equation, along with the constraint equation, it will end up giving you 4 equations in terms of 4 unknowns, the x, y, z, and lambda. And the best thing we could do is just kind of illustrate once again how this works in a nice concrete example. So the problem at hand is an ideal scenario for us to use Lagrange multipliers. And to start, what we'd like to do is just simply write down the Lagrange multiplier equation. That would be the gradient of A is lambda times the gradient of V with x, y, z equal to 4. And recall, as we mentioned in the previous video, when you think about this gradient vector, what we really have is ax, ay, az equals lambda times vx, vy, vz. And if we equate together these components, we end up with 4 equations. We have ax is lambda vx, ay is lambda vy, az is lambda vz, and lastly the constraint equation xyz is equal to 4. And let's go ahead and once again put these in terms of the specific functions of interest we have. Looking at the function a and v, we have the following partials. A sub x is 2y plus z, which is equal to lambda v sub x. Similarly, a sub y is 2x plus 2z, and that's equal to lambda times v sub y, xz. And then lastly, az is 2y plus x, and vz is xy. And then we have the constraint xyz equals 4. And this is really what we will think of as kind of the starting point of using Lagrange multipliers. Recognize we're in kind of this appropriate scenario, a function to maximize or minimize relative to a constraint, starting off with this gradient equation and then breaking it down into its specific components. And the overall goal at this point is to work with these first 3 equations, and I'll just simply refer to these as the gradient equations, until we have something to plug into the constraint. And this is really where we encounter, I'll say, the difficulty of the problem. And what makes these kind of difficult or interesting is the idea that there's no one technique or method that I can guarantee you that will always work. Instead, based upon our experience from practicing multiple examples, we should be able to formulate an approach similar to what we've seen in the past. And at this point, we've really seen one method that was applied in the previous video to our first example. And that method doesn't apply here. It really relied upon just taking one equation and solving for any quantity that you could. And there's just not much information to get from a single equation here. So instead, we're going to approach this from an alternative perspective and develop a new technique which you can apply in the future. The idea is going to be that in each of these three equations, lambda is representing the same value. So let's solve for lambda in multiple different ways and see what that gives us. So the whole goal or technique is to solve for lambda. If we solve for lambda in the first equation, we would have 2y plus z over yz. If we solve for lambda in the second equation, it's the same lambda, and that would leave us with 2x plus 2z, all divided by xz. And in the third equation, 2y plus x over xy. And at first glance, it's not clear kind of how we can use these equations, but let's go ahead and make a very nice observation. If I just focus in on these first two equations, and while we're at it, we go ahead and we simplify. We can break a fraction up over addition in the numerator. So we would have 2y over yz plus z over yz is equal to 2x over xz plus 2z over xz. And I realize my 2's and z's do look an awful lot alike, but hopefully you can distinguish them by the horizontal bar. And notice all of these cancellations. Y, zz, xx, zz. So we end up with 2 over z plus 1 over y equals 2 over z plus 2 over x. And now we once again see the cancellation, a 2 over z and a 2 over z. And if you cross multiply, what we end up with would be an x on the left and a 2y on the right. Which certainly brings us closer to the point of substituting some quantities into the constraint equation, as we can replace x with 2y. But before doing so, let's go ahead and also see what the rightmost two equations would tell us. And if we do the same exact approach, break them up into two fractions and simplify, in the middle we would have 2 over z plus 2 over x. And note, that's exactly how we simplified that left term a moment ago. And then for the right piece, if we cancel off the y's in the first, so 2y over xy, that would leave us with a 2 over x, plus x over xy leaves us with a 1 over y. So 2 over x cancels. And if we go ahead and cross multiply, we would end up with 2y equals z. And we are now in an ideal scenario. We have x is equal to 2y, which can replace the x in the constraint equation. Z is also equal to 2y, which can replace the z in the constraint equation. And when you make those two replacements, the equation only involves y's, and it's something that we can work with. So now if we go ahead and we follow through with this suggested technique, substituting into the constraint our entire goal, so that's x, y, z equals 4, gives us the following. We have 2y times 2y is all equal to 4. So note, the z became a 2y and the x became a 2y. And when we've done this, you have 2 times 2, which is 4, on both sides, which gives us y cubed is 1, which implies y equals 1. And what we are doing is now trying to figure out what the corresponding x and z values would be for that value of y equals 1. And we don't have to look far. We know that x is 2y and z is 2y. So what we end up with now is x is equal to 2y, which equals 2, y equals 1, and z equals 2y, which is equal to 2. And we have the point 2, 1, 2. And this gives us a potential location for an absolute maximum or absolute minimum corresponding to the function a. Now, the question becomes, is that going to be an absolute maximum or an absolute minimum? So in order to tell, we need to do a little more investigation. We need to know what is the value of a at this input of 2, 1, 2. And if we substitute that into a, we end up with 12. And if I know this is going to be an absolute max or absolute minimum, which we do from using the method of Lagrange multipliers, we can check this by evaluating a at any other point which still satisfies this constraint equation. So a very simple point I can come up with satisfying that constraint equation is to make two of the variables 1 and the other variable 4. And if you substitute all of those into the function a, you end up with a 17. So at this extreme value location, our output is 12, which is smaller than 17. And that guarantees for us that we will have an absolute minimum. Which completes this current example, but remember kind of the big takeaway is once we write down these equations to work with, you want to get enough information from the gradient equations so that you can substitute into the constraint. Whatever points you come up with, those would be the potential locations of absolute maximums and absolute minimums. If there was an entire list of those points, then we would go through and evaluate the function at each of them and pick the smallest and the largest outputs. Let's look at one more example. For this example, we will find the extreme values of the function f on the circle x squared plus y squared equals 13. And just for good practice and to make sure we're keeping up to date, if I was to write down this equation z equals 4x plus 6y, which would be a surface representing the graph of the function f, can you describe that surface in one word? Hopefully the answer is yes. This is a plane, just as a reminder. And what we're trying to really determine is, at what points on this plane, sitting above this circle, will we have those extreme values. And this is the ideal scenario to apply Lagrange multipliers. Maximize and minimize a function relative to a constraint. So note, in this case, g of xy, our constraint function, is x squared plus y squared. So let's go ahead and write down the equations to work with from Lagrange multipliers. From Lagrange multipliers, we have as our starting point, the gradient of f is lambda times the gradient of g, with the constraint x squared plus y squared equals 13. And this will give us the following three equations. So from the partials with respect to x, we would have f sub x is equal to lambda g sub x. F sub y is equal to lambda g sub y. And we have our constraint. Now remember what our goal is. Essentially what we would like to do is determine enough information from these gradient equations to substitute in to the constraint. And at this point we've seen two techniques from our previous two examples, and I think both of them could be reasonably applied, but I'm going to go about this just a smidge differently to illustrate maybe a slightly different perspective. So what I'm going to note is that if we were to look at these first two equations, in the first equation you can solve for x. If we divide both sides by 2 lambda, we would have 2 over lambda is x. In the second equation, if we divide both sides by 2 lambda, we have y is equal to 3 over lambda. And that gives me enough information to substitute those values into the constraint equation. And that's kind of our goal. So substituting into the constraint, we would have x squared plus y squared is 13. So working through this, 4 over lambda squared plus 9 over lambda squared is 13. So that 13 over lambda squared is 13. And lambda squared is equal to 1. So what we have done is we've solved for x in terms of lambda and y in terms of lambda. When we substitute those into the constraint equation, we have a single equation only involving this quantity lambda. We solve and we get two values. But if we look above, each of those values of lambda will correspond to a point. So let's see here. When lambda is equal to 1, we have x is 2 and y is 3. And when lambda is equal to minus 1, we have x is minus 2 and y is minus 3. And these are the locations corresponding to potential absolute maximums, absolute minimums. We evaluate the function at each of these points. The biggest output would correspond to the absolute maximum. The smallest output corresponds to the absolute minimum. So f of 2 comma 3 is 26, whereas f of minus 2 comma minus 3 is equal to minus 26. So we have our absolute max and our absolute minimum, which completes the problem. And let me just finish by noting kind of what type of work and organization you should use. So roughly speaking, if you ever go about a problem and organize it and show your work as I have done, I can hardly complain. At a minimum, you should write down all of these Lagrange multiplier equations, kind of clearly show how you're working with those gradient equations, and then end up by substituting in to the constraint, then taking whatever information you get back to list your points and evaluate your functions at those points. Simply write next to the biggest one, absolute maximum, and circle it. Next to the smallest, write absolute minimum and circle it. That gives us a solution. So remember, there are plenty of good suggested problems for you to kind of further explore these techniques. I highly recommend doing so, as they require practice, which we will get in a few more videos, and it's also something that wouldn't be surprising to encounter again. So with that, stay tuned and take care.